So we're going to work an example. We went through the procedure to solve for the convection coefficient for cylinders last time. So we'll work the example today. We're going to start off with three cases. Case A. Case A is a circular cylinder. Diameter 1 centimeter. The length is into the board. It's not given. The fluid approaching the cylinder is air. Free stream velocity, 15 meters per second. Free stream air temperature, 25 degrees C. And we're going to be asked to find Q. So I'll just put it right here. Find QF, or Q prime. We don't know the length, so we make it prime. So now it's going to be in watts per meter. Our answer is in watts per meter. The way we start this, and you know from last time, we have to calculate the properties. And the properties depend on the film temperature. Film temperature is the surface temperature plus the free stream temperature divided by 2. And let's see, surface temperature is 75 degrees C. So we've got 75 plus 25 divided by 2, 50 degrees C. In the back of the book, table A4 for air, 323 K. Properties in table A4. Okay, so we can get those properties. In cases like this, we said last time, what you want to calculate first is the Reynolds number based on diameter. Okay, so U infinity, 15. Diameter, 1 centimeter. Divided by nu from the back of the book. Reynolds number based on diameter, 8,108. Now, we said that there are three possible equations to solve for H. The Hilbert, the Zukakis, and the Churchill. And we said in this class, for homework and exams, we're going to just use the Hilbert one, the simple one. Even though it's outdated, it's not off by a tremendous amount. We'll use it because we don't need to correct for properties like the Zukakis does. So we're going to use Hilbert equation. That is, let's go back and see where that is. Chapter 7. Hilbert is 744. Yep, 744. If we use that, we have to, well, I'll write it down first. Nusselt d bar h bar d over k, c Reynolds d to the m, Prandtl to the 1/3. So we're going to get the constants C and D, or C and M, pardon me, from table 7.2. C 0.193, M 0.618. Remember, that table has a Reynolds number range, and you find out where your Reynolds number falls in that range, and then use that C and D. It's a piecemeal curve fit of experimental data. Doing that, gives H bar, I know K, I know D, I know Reynolds number, Prandtl number 0.7 to the 1/3, C and M right here. Put the numbers in there, and we get H bar 125. Now we want Q. We want Q prime, which is Q over L. Q is equal to our H bar surface area times T S minus T infinity. Surface area of a cylinder. That's the area of the cylinder touching the fluid, air. Circumference, pi d, times length, L. Pi d L. The L's cancel out. So Q prime, H bar 125, pi d 75 minus 25. 196 watts per meter. Okay, so that's solving a problem to find H for a circular cylinder using the Hilbert equation. All right, now let's take case B. Okay, case B is going to be a square tube. Square. And this particular case, this is case B. 1 centimeter. One centimeter. And again, we have an approaching free stream, air, with the same U infinity, the same T infinity we had before. Okay, and we want to find Q prime. All right. Number one, properties. Okay, properties, T-film. Same thing, 50 degrees C, 323 K. Reynolds number, based on D. Okay, have to shift gears. D no longer stands for diameter. This is not a circular tube, it's a square tube. The picture in the book shows you that D is the distance from the top to the bottom of the geometry. Looking forward from where the air approaches it, what do you see? I see top to bottom, 1 centimeter. D is 1 centimeter here, over here. D is 1 centimeter here. Conclusion, the Reynolds number stays the same. Reynolds number 8108. That D for this picture, 0.01, 1 centimeter. Now, here's what the rule said. The rule says if it's a non-circular tube geometry, so non-circular tube, we're going to use Hilbert equation, but we get C and D, or C and M, pardon me, C and M from table, a different table, C and M, table 7.3. Yeah, question? Okay. Okay. I'm going to put that up there for you just so you know what those two guys are. So C, M for this one, case B, 158, and M 0.660. Okay, so for this case we get again, use Hilbert. Okay, there's Hilbert. H bar equal K over D, C Reynolds D to the M, Prandtl to the 1/3. Put those numbers in there, you know them all. D is wherever you see a D now, D is 0.01. Where does D appear? It appears in the Reynolds number. It appears in the Nusselt number. So put 1 centimeter. And for H bar for this geometry, 149 watts per meter squared. Okay. Now I want Q though. I don't want H bar. The end result, I want Q. So same thing, Q prime, Q over L, H bar pi D, Ts minus T infinity.
It would be.
Oh, which one? Oh, thank you. Good point. Now, what is surface area? Surface area is the area of the tube that touches the fluid air. Okay. Front, back, bottom, top. Okay. 4 times that distance. 4 times 0.01. Times L. Times L. And then divide by L. The L cancels out. Okay. 374. Let's see, H bar, nope. 300. 300 watts per meter. Okay. Now we'll do a case C. Case C, what I'm going to do now is I'm going to rotate that square tube by 45 degrees. Rotate the square tube by 45 degrees. So now the point is facing forward. This is still 1 centimeter and 1 centimeter. It's air still, of course. The temperature of the air is 25 degrees C. U infinity, 15 meters per second. And of course, in this picture here, I didn't put it on here, but again, T surface is 75. In this picture here, T surface is 75. Okay. Start again, same procedure. I've got to find properties. At what temperature? TF. So properties. At TF. 50 degrees C. 323 K. Got them? They're all the same. Properties here, 323 K. Properties here, 323 K. Properties here, 323 K. I need that to get the Reynolds number, first of all. Reynolds number based on D. U infinity, D over nu. U infinity is my 15. Kinematic viscosity didn't change. 18.5, 10 to the minus 6. D is not a diameter. D is a distance. What distance? In the book, it shows you the distance D is a distance from the top to the bottom of what the air sees approaching the tube. That's D, the distance from the top to the bottom of what the air sees approaching the tube. What is D? The hypotenuse of a right triangle. 1 centimeter times square root 2. Okay, 1 centimeter times square root 2. New Reynolds number now. It's no longer 8108. It's the first two. This one, the new Reynolds number, 11466. Okay. Again, we're using non-circular tubes. Again, we use the Hilbert equation. again, we use table 7.3. So from table 7.3, C equal M equal. All right, let's see what C is, 0.304. M is equal to 0.590. We still use Hilbert right here. H bar equal K over D. C, Reynolds number based on D to the M power. Prandtl to the 1/3 power. Wherever you see a D, put the D from the picture. Square root 2 times 0.01. If you do that, you get 187 watts per square meter K. To get Q prime, Q over L. Okay. H bar times the surface area. There are 4 sides touching air. Each one is 1 centimeter. Multiply by L, divide by L, times Ts minus T infinity. Q prime, 374. Okay, 374. So, you've got a 1 centimeter square tube. You want good heat transfer. If you put it with the flat side facing forward, you get 300 watts per meter. You put it with the point facing forward, whoa, it goes up by 25%. 25% more heat transfer just by turning the tubes 45 degrees. That's why you should always check things like that, especially for non-circular tubes. And of course, it's pretty much explained by fluid mechanics, ME312 stuff. When the flow hits B, or the flow hits C, it hits B, stagnation point, goes around here at the corner, top and bottom. Separation, it can't make a sharp right turn. Separation. Region down here, turbulent region here. Here, stagnation point right there. Maybe we get a laminar boundary layer starting to build up here and here. It might transit to turbulent, but let's just say it'll probably stay laminar. At this point, it breaks off, of course. It can't make a sharp right turn. Now, in heat transfer, you'd rather not have a wake region. This is called a wake region. This is a wake region. A wake region is where the flow is rather random. There are circular turbulent eddies in that region, but there's not good fluid flow. You ever, if you own a van or know someone has a van, look at the back window on most vans. They're always dusty. They're always dusty. I've got one, I have to clean it once a week. It's always dusty. Because here's the van. Here's the back window. These little dirt particles from the air are circulating. They attach themselves to the back window. My front window never needs to be wiped hard unless it rains or there's fog. The front window is much, much cleaner than the back window because this velocity sweeps any dirt off the front windshield. But on the back, you don't have that. You've got a turbulent wake region. So the dirt sticks back there. And you've got to wipe that window every time you buy gas or whatever. Yeah, that's the story. And that means you've got poor heat transfer. Because if the air is not moving, I guarantee you the heat transfer is not very good. You want to face a fan and cool yourself? You can do it one of two ways. Lay flat on the ground with your hands like this, face the fan. Or stand up like this. Guess which way cools you the fastest? That's a no-brainer, obviously. Did you ever see a picture of a buffalo in a snowstorm? A buffalo in a snowstorm, blowing blizzard in Montana, blowing blizzard. The buffalo didn't take this class. He's not a mechanical engineer. He could be. I'd probably pass him. He's so smart. But do you think the buffalo stands sideways to the wind? Oh, no. I'll tell you what he does. He faces the wind, and he puts his head down. Why? Because the smaller cross-section area means he won't be losing heat as rapidly. Oh, yeah. Pretty smart move. That's what you want to do. A lot of things are explained by fluid mechanics, okay? This guy here, look how small the wake region is. Look how big the wake region is. Oh, the front of this guy here has really good heat transfer. But that's only one surface out of 4. Look at this one. 2 out of 4 have bad. 2 out of 4 have pretty good heat transfer. So that's why this guy wins right here, explained by fluid mechanics. Okay, big long story, but just so you know. If you want to redo this guy here and you say, you know what if I, part A, what if I want to use the Dukakis equation? Okay, the Dukakis, let's see where it is here. Equation 745. You would get an H bar of 145. They're off by 15 to 20%. Yeah, I know, because one's 1933 instrumentation and one's 1972 instrumentation. I expect them to be different. So we're not going to use that in this class I told you, but just so you know, you can get H bar a couple ways from the church, what's our first one there? Hilbert, or equation 745 Dukakis, or if you want to do the one Churchill, you don't need to use a table for it. One equation fits all. Then that'll give you a different H bar. So the H bar will change. Don't expect them to be the same. They will change. All right, any questions on this before I erase this and start another example? Okay. Now, this example is going to be a pin fin. Let's see, from cylinders, example, okay, pin fin. So, I'll give you the picture. There's this circular pin fin attached to a base material. So this is the base. This is the fin. 12 millimeters and diameter is equal to 2 millimeters. Okay, the base temperature is given 350 Kelvin. T base equal 350 Kelvin. There is an air stream approaching this air. The temperature T infinity is known, and U infinity is given. T infinity 300, and then 10 meters per second. So air blowing over a pin fin. The base of the pin fin is 4 millimeters on a side. It's a square base. And we're asked to find Q total, which is the fin plus the base. The total heat transfer from the fin and the base. Okay. We'll do the fin first. All right. The fin's a circular cylinder. Okay. There was a problem just about like this. It was in the fin chapter, chapter 3. In the fin chapter, chapter 3. Almost identical to this. The only difference was in chapter 3, they were really kind. They said, oh, by the way, the value of H is 125. That's not the real world. Nobody's going to give you H out there. They're going to say, boss, do you know H for this thing? No, he's going to say, where'd you graduate from? Tell him, well, don't tell him Cal Poly Pomona, okay? Just Anyway, this is a chapter 3 problem and a chapter 7 problem wrapped into one. When I solve this problem, I'm going to start reviewing for the final because I'm going to go back now and go over fins in chapter 3. I'm going to do that for the next 2 weeks when I work problems. I'm going to try and go back and pick up stuff we did back then to review. So this is our first start of the review for the final. Okay, Q fin. All right. Let's go back and first of all get the properties. We always start with getting the properties. This is going to be, okay. I know that in chapter 3 with a fin I had to have H. If H wasn't given to me, I couldn't solve the problem. We're in chapter 7 now. If they don't give you H now, you can solve the problem. Okay, I got to find H. What is this thing? A circular cylinder in cross-flow. Okay, great. What do I do about a circular cylinder in cross-flow? We just did it 3 times. Number 1, get the properties at T film. Okay, T film equal T surface plus T infinity divided by 2. The first question you have is, what's T surface? Now, I'll tell you what you're given. You're given T base, and you're given the air temperature. But when you work chapter 7 problems in circular cylinders, they always give you T surface. Well, that's the real world. Sorry about that. I don't know right now. I can't tell you what TS is. As a matter of fact, I know it changes. It starts out down here at T base and ends up here at some other temperature. I'll just show you how it varies. This is a review of chapter 3. Okay, here is the length of the fin, L. Here's T infinity. Here's T base. T base, 350. T infinity, 300. This fin's losing heat by convection. Okay, I know what the shape is. It looks like this. There's a plot. Now, I don't know where that guy ends up at L. I don't know where he ends up at x equal L. Okay? Maybe he ends up down here at 300. Maybe. Or maybe he ends up here at 340. Maybe. See, I don't know. Well, if you don't know, guess what you're going to do for TF? I'm going to take what I do know. The base is 350, the air is 300. My first guess, and it's a guess, my first guess is 350 base plus 300 T infinity divided by 2. 325K. I know that's not right, but I got to start somewhere. Guess what I have to do? Oh, in the real world, I have to iterate. I guess again and guess again until it converges to a solution. But I'm not going to do that, but I'll tell you that's how it goes. Okay, TF, get the properties. I'm not going to put them down. We got the properties. Back of the book under air, table A4. Next step, chapter 7. Get the Reynolds number. Okay, Reynolds number based on D. U infinity d over nu. I'll put the numbers in here. 10 times 0.002 kinematic viscosity, 18.4, 10 to the minus 6. Reynolds number, 1,088. I'm going to use Hilbert because that's what I said we do. So use Hilbert. Get C and M from table 7.2. And the value of C, 0.683. The value of M, 466. And then Hilbert, H bar, and we have our D, so our D goes down here, our K goes up here. C, Reynolds, D to the M, Prandtl to the 1/3, Prandtl 0.7. Get K, the back of the book, get the viscosity back of the book. You got C and M, put them all in there one more time, and you get H bar 221. Okay? All right. Now we're done with chapter 7. Now it's a chapter 3 problem. Now it's a chapter 3 problem. How do I solve a fin, circular pin fin stuck to a base where H is given to me? Because I know H now, it's 221. Chapter 3 before, we had to be given H. We couldn't find H. Okay, back to fins. Let's see. I think what I'll do first is I'll try and look at table 3.4. Table 3.4. Okay, uniform fins. Okay, there were 4 cases. Case A, B, C, D. There was a temperature 1, T minus T infinity over T base minus T infinity. And then there was a Q fin, heat lost by the fin. Okay, I want to find Q lost by the fin. Okay, case A, convection at the tip. Case B was adiabatic fin, adiabatic tip. Case C, given temperature at the tip. Case D, infinite fin model. Okay, let me go back to table 3.4. There it is. E to the minus mx, capital M. This guy up here, I'm going to put this equation here, right up here. QF fin, capital M, hyperbolic sine ML. H over MK, H over MK. Hyperbolic cosine ML. Divided by cosh ML plus H over MK sinh ML. Right. I'll put this guy down just so it's complete. This guy, t minus t infinity over t base minus t infinity. M times sinh m, oh, that's qf, pardon me, cosh m L minus x plus h over mk sinh m L minus x divided by cosh ml plus sinh ml. Okay, there they are. Now, I know it's not a case B. It's not an insulated fin tip, no. I know it's not a case C. Nobody gave me the temperature at the fin tip, no. I got two possibilities, case A and case D. Oh, it's definitely a case A. There's convection from the fin tip. There's definitely convection from the fin tip. It's definitely a case A. But I may want to check case D. Why? Look at the two equations. Can it be any easier than Q equal M, unless you want to go through this thing up here with hyperbolic functions and risk making an error? Oh, there's no comparison. That's why there's a case D in table 3-4. That's why they put it in here. Because if you qualify, you get to do the easy calculation. If you don't qualify, you got to do the tougher calculation. So how do we do that? Can we use case D? All right, check for case D. Is ML greater than or equal to 2.65? If it is, I can use a simple case, case D. Okay, next step. Find M, little m, the square root of HP over KAC. Okay, the perimeter, obviously, pi times d. As we said in chapter 3, you've got A sub C, you've got A sub F, you've got A sub P. Boy, you better know what those mean, because they're critically important in fin analysis. A sub C, it's not convection. That's the cross-sectional area, pi r squared, circle. A sub F is the area of the fin that's touching the fluid, pi dl, pi dl. A sub P, the profile area. Look at the side view. There it is. What do you see? I see L times diameter. L times diameter. Okay. Okay, anyway, that's A sub C, cross-sectional area. Pi d squared divided by 4. P, the perimeter, pi d. Put the numbers in there. Where's H? I got H from chapter 7. It's right there, 221. Put it in there, little m, 33.1. Multiply little m times L. .1. The length of the fin away from the base is 12 millimeters. And so I end up with 0.40. Not greater than 2.65, so cannot use case D. All right, got to use case A, the tough one. Yep, so use case A. Okay, there it is, case A. QF, got to find capital M. Okay, put capital M here. Here's capital M, there's little m. Okay, capital M, square root H, P, K, A, C times T surface minus T, this is my base, T base minus T infinity. I just told you what the perimeter was, and I told you what A sub C was. Put the numbers back in the equation again for capital M, and you get capital M then comes out to be 2.07. All right, now I've got capital M, that one. Now I've got little m, there, and there. Now I do the long calculation. If I do the long calculation, put everything in there, I get 0.815 watts. So that fin's losing 0.8 of a watt. Okay. Now, let's go back and see. We're supposed to find Q total. Okay. Q total. Q fin plus Q base. So we'll do Q base right here. Okay, there it is. Convection heat transfer, Fourier's law, chapter 1. Mm-hmm.
Does your H bar change?
We'll come back to that one. Good question, but hang on, okay?
All right.
All right. We're going to use the same H bar, okay? H bar, there it is, 221. Equal 221 times our base area. Now we have to get the base area right. The base area, I'll kind of shade it here. Here's the base area. There. The area that touches the air. Air area. 0.004 squared minus pi d squared divided by 4. 0.004, that's the square area, minus where the fin is. So pi over 4 d squared. Diameter was 2, yeah. Times the temperature difference, 350 minus 300. So, Q base equal 0.140. Okay, Q fin, 815. Q base, 140. Q total, 955. Almost 1 watt. Almost 1 watt. Yeah, we're assuming the H didn't change. Of course, that's suspicious. I'm sure it does. Because this plate is not getting the full impact of the air. So maybe you want to use the first part of Chapter 7, flat plates. We wouldn't get that sophisticated in this class, but that's what you probably want to look at. These fins would be mounted on a flat plate. Try and get some estimate of what that H-bar might be over a flat plate with fins attached to it. It's not an easy calc. We will assume it's the same, though, in this class, okay? Yeah.
How come you wouldn't find T surface using the middle column?
This one. This one?
Yeah, to use the T in order to get the T surface of the fin.
It's a good question. I'm going to do that right now. That's right. There's a lot of questions about those H's, okay? This is ME 415, not the master's program EGR 535, okay? This is the undergraduate course. So, but I'll just tell you another story too, is that, you know, if you're putting these pin fins, let's say let's say the guy tells you from electronics, says, okay, my electronics are generating 100 watts. I've got to get that heat out, otherwise the box starts to build up in temperature and my electronics prematurely fail. So I need to get that heat out of that box. Say, okay, you're the mechanical engineer, can you do that for me? You say, yeah, okay, I'll do it. There's my pin fins. I attach them to a base, maybe, you know, 40 centimeters, 40 centimeters. To dissipate 100 watts, just a real quick calculation, I think I probably need times 195, about 110, 120 of these pin fins on that sheet of metal. So I need that many pin fins on there to do the job, I think. Okay. Yeah, that's true, but then of course, we didn't cover this in this class. There's a section in our book, but it's these circular tubes arranged on a here they are arranged on a plate. And the air comes this way. And the air hits this first one, and it looks just like the picture that I showed you before. It looks like that. And this one here, and it looks like that. Bad news, bad design. This guy here, what does he see approaching him? Stagnant air, turbulent eddies, like this. Is that good? Oh no. You want the approaching air to hit it like this. So rather than this, what do? You stagger the tubes. You put this tube where the velocity is the biggest, right here. And now all this air is coming down here. Bam, hits that tube. Good, good. Same thing here. Move that tube down to here. Now leave that tube where it is. Now it breaks up here and here. And now this is the big velocity right there. So that's a whole other part of heat exchanger design, okay? It's called staggering the tubes, how you get the most efficient heat transfer. Okay, but just so you know, and those H's, they're not as simple as this, where one fin is normal to the tube flow. It's not quite that simple over there in heat exchanger design. It's a big, big topic. One time when the Fluor Corporation was in Irvine, they called us here and said, would you guys mind teaching a graduate heat transfer course on heat exchangers down here for our engineers so they can become more knowledgeable? Because after you finish this class, you've had, what, 1 week, 65 minutes times 3 on heat exchangers? You're not the experts yet, okay? So yeah, we went down there with the graduate program. They got graduate credit if they wanted it, but we taught a full 1/4 course, 4 hours a week, down there after work for them, and it was titled Heat Exchanger Design. And their engineers, mostly MEs, went through that to make them more proficient in heat exchangers. So yeah, it's a real complex topic. It requires a lot of work. It's not very simple. Back to here. Okay, is there any other way to solve this? Yeah, let's review chapter 3 again. Are there any graphs we could use? There was circumferential fins, there was rectangular fins, and there was triangular fins on the graphs. Nope, nope. This is the pin fin. Can't use the figures in that chapter. So far we've used table 3.4. Now there's another table, table 3.5, which gives us the fin efficiencies. Okay, this was the geometry, and this was the equation for the fin efficiency. And once you got the fin efficiency, then this is what you did. Okay. There's about 6 or 8 pictures in there. Only 6 or 8. But lucky for you, if this is your problem, one of those pictures looks like this. Yeah, pin fin. It's in there. And A to F, hyperbolic tangent. of MLC divided by MLC. In the picture here, he tells you L sub C equal L plus D over 4. He tells you what L sub C is in the table 3.5. So it's equal 12 millimeters plus 2 divided by 4, 12.5 millimeters. L sub C. What's L sub C? The corrected fin length. What's A sub C? The cross-sectional area. Can it be confusing? Of course it can. Of course it can. You've got to get those definitions straight in your mind. What is L sub C? Corrected fin length. What is A sub C? Fin cross-sectional area. Now, this looks a lot easier than that looks. So I think if this was my problem, I'd work it this way. I don't mind finding one hyperbolic function compared to 4. Okay, it's your choice though, take a choice. You can work it from table 3.4 or table 3.5. Put this up here, put it in here, you'll get an answer very close to our answer here. Okay, there, 815. Let's say that the fin didn't look like, well, let me back up and answer your question. All right, here's what you do in the real world. When you're done with it, you should say, you know what? What if somebody asked me on an exam or a final to find the temperature at the fin tip? Okay, it's fair game, of course it is. There it is, table 3.4. There it is, right there. T, where? X equal L. Here, what do you put here? X equal L. Cosh, 0, 1. X equal L. Cinch, 0, 0. Plug them in here. Now you've got T at the tip of the fin. Now maybe you want to go back in here and change this surface temperature to be T base plus T tip of the fin divided by 2. Put a new TF in here. All right, everything changes. The Reynolds number changes, the C's and M's change, the H bar changes, the M changes, the little m changes. Go through it one more time and get a new H. Okay, then put the new H in here and see what the new temperature of the tip is. If it didn't change by more than 1 or 2%, stop, you're done. If it did change by 5 or 10%, do it again until it converges. In our class on exam, no, you do it once. Tell me what you assumed, and it's critical you tell me what you assumed, and then go ahead and work it. I mean, you wouldn't be totally incorrect if you just used 350, but I know it's not a good guess. So if you want to iterate a long time, guess 350. If you want to have fewer iterations, guess 350 plus T infinity divided by 2. Okay, now, let's see, we got that. All right, now let's say that I'm thinking about, as I told you, I get a lot of my problems for exams from working problems on the board or homework. I say to myself, you know what? I spent a half hour in class going over this problem here. I think what I'm going to do for our next exam, I'm going to make this thing a square one, 2 millimeters on the side. And see if they can solve this one now, because I spent a long time on this one. Okay, let's go through it. Okay, let's do the easy way. First of all, there's no figures. Figures don't work. Okay, this is not infinitely long. Is it in table 3.5? No, it's not. No, it's not. No, it's not in 3.5. Okay. Is it in 3.4? Answer this question. Is it uniform area? Yes, it is. What does that mean? That means the cross-sectional area does not change as you go along the length of the fin. The cross-sectional area does not change as you go along the length of the fin. This problem here, slice the fin normal to the axial direction. Here, 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 here. What's A sub C? Pi r squared. Did it change? No. I can use table 3.4. This fin, slice it here, 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 here. What's A sub C? 2 times 2 millimeters. Did it change? No. I can use table 3.4. I can't find it in table 3.5 though. Gone. Here it is. You might want to check for case D first. If the answer is no, go to case A. There are the equations. Okay, so you can do it that way. Let's say it's the final exam, and you see this problem on the final exam. Conical pin fin, a cone. Conical pin fin. Oh, it's in, good for you. It's in table 3.5. Is it not in any figures, but it's in table 3.5. Yes, it is. In the figures? No. In table 3.4? Answer this question. Cut the fin normal to the axial direction and ask yourself if the cross-sectional area changes. Oh, dramatically. Pi r squared. R decreases as the length goes up. Conclusion, I can't use table 3.4 to solve for Q. So you see how things change. It depends on answering a few questions like that, okay? All right, so that is that. Let's see, anything else we have to discuss on this one? Okay. No, I don't think so. All right, one last thing. All right, let's look real quick. I'm going to look at a problem. When you're designing heat exchangers, you have tubes. Oh, maybe it's in a condenser. Okay, and you've got cold water in the tubes, and you've got steam coming out of the turbine or something like that. It could be a number of different cases, but let's take a look real quick at cross-section of the tube. This is the tube material K. Okay, this happens every time. Okay, I'm going to put this down here again. Q fin equal, this is for infinite fin, case D, but it's typical for all cases. Let me go back to my problem again. Wow, you better be careful. Man, you better be careful. Because I know it always happens on an exam. I hate it because I hate to take points off for it. But what can I do? In the problem I just worked, there are 2 Ks. You have to get those guys straight in your mind. I didn't tell you this, and I should have. I forgot to. But that bin is copper. So anytime you're working with the spin equations, what's that, chapter 3? K is K of the material of the fin. Chapter 7, what is K? K goes with the film temperature of the air. Boy, be careful. In a rush, when you're under stress, you do make sometimes silly mistakes. That would be one classified as a silly mistake, but it's still a mistake. So watch out when you do these problems where there's 2 values of K in them. The K of the material, copper, and the K of the air, and the other. Mm-hmm.
So just to be clear, when you're solving for M, you use K of material.
Yeah. Okay. All right, back to here. This is a cross-section of a tube. On the outside of the tube, there's a convection coefficient, H outside. Temperature out here is T infinity outside. inside the tube is carrying a fluid maybe. Temperature is T infinity on the inside. There is an H on the inside. And then there is a K of material. And so when you look at chapter 3 again now, go back and review chapter 3 real quick. 2 minutes. What's this resistance? 1 over H inside, A inside. Natural log, R outside over R inside, 2 pi KL. This one, 1 over H outside, A outside. This one, T infinity on the inside. This one, T infinity on the outside. Hot stuff in the tube, there's Q. All right, this is like chapter, there's a problem like this in chapter 3. I assigned it for homework. But in chapter 3, guess what? They gave you H outside and H inside. That's not the real world. Nobody does that. You're the mechanical engineer. You got the degree in your hand. You figure it out. Okay. This guy here, chapter 3. The resistor picture, chapter 3. Reviewing. This guy here, I need H outside. Okay. There it is. Chapter 7. This guy, I need H inside. Chapter 8. Coming up Monday and Wednesday next week. Yeah, you see how we lump this stuff together near the end? All the pieces come together. Chapter 7, Chapter 8, Chapter 3, all together. It's comprehensive, it has to be. That's the way heat transfer is. Okay, good stopping point, so we'll see you then.